Right now, while you're lying here, rivers of ice are moving across Earth. Glaciers, flowing slower than you could ever see, but more powerful than almost anything alive. Tonight, we drift into their world. A single glacier can hold more water than all the rivers in your country. And they make sounds, deep groans, quiet cracks, like the earth is breathing in its sleep. This is your place for calm curiosity, a quiet hour to explore something beautiful and ancient while you settle into rest. So get comfortable. Let your body sink into wherever you are, because we're about to discover what happens when snow refuses to melt for 100 years. It starts with snow, simple snow, falling from the sky in a place cold enough that it doesn't fully melt. Maybe high on a mountain, maybe near one of Earth's poles. The snow lands soft and white, the way snow always does. Then winter ends. Spring comes. But not all the snow melts. Some of it stays, a layer of white covering the ground, waiting. Next winter, new snow falls on top of the old snow. The bottom layer gets pressed down by the weight above it. It becomes denser, tighter. The fluffy crystals start to change. This happens year after year, snow on snow on snow, each layer pressing on the ones below. The weight squeezes out the air between the crystals. What was once light and airy becomes heavy and compact. The snow transforms into something called firn. That's the in-between stage. Not quite snow anymore, but not yet ice. Think of it like making a snowball. You pack the snow tight in your hands. The air escapes. The snow becomes dense and hard. But imagine doing that for decades, for a century, not with your hands, but with the weight of hundreds of feet of snow pressing down from above. The firn keeps compressing. The crystals grow larger as the smaller ones disappear, their molecules joining with bigger crystals nearby. The air pockets get tinier and tinier. Some get sealed off completely, trapped as bubbles. After about 50 to 100 years, the transformation is complete. What started as soft snow has become solid glacier ice. Dense, heavy, blue in its depths. This ice is different from the ice in your freezer. It's denser, more compressed. It can be hundreds or even thousands of feet thick. And here's the thing, this process is happening right now. Somewhere on Earth, snow that fell this winter is beginning its slow journey toward becoming glacier ice. Snow that fell when your great-great-grandparents were young might just now be turning into true glacier ice. The timeline is longer than a human life. You could stand on a glacier every day of your life and never see the snow at the surface become ice. But it's happening, patient, inevitable, following the simple laws of pressure and time. If this brings you calm, I hope you'll subscribe to Simple Science for Sleep. Join thousands of others who drift off to these quiet science journeys each night. And tell me in the comments, where are you listening from tonight? What time is it there? I love knowing we're all scattered across the world, lying in the dark, exploring glaciers together. Maybe you're in Australia where it's morning, or Europe where it's the middle of the night, or somewhere I've never been. Say hello, I'd love to know. Now, back to our ice. Some glaciers form on flat land near the poles. These become ice sheets, spreading out in all directions like frozen lakes. The ice sheets covering Antarctica and Greenland are like this, miles thick, covering entire continents. Other glaciers form on mountains. Snow collects in a bowl-shaped area near the peak. Year after year, it builds up. When there's enough weight, the ice begins to flow downhill. These are called alpine glaciers or mountain glaciers. They follow the valleys like frozen rivers, carving their path as they go. The ice needs two things to become a glacier. First, more snow has to fall each year than melts. That's how it builds up. Second, it needs to be thick enough to flow under its own weight. That thickness matters. A few feet of old snow won't flow, but get 100 feet, 200 feet, more, and something changes. The pressure at the bottom becomes enormous. The ice at the base starts to behave less like a solid and more like a very, very thick liquid. It's still frozen, still solid if you touch it. But at the molecular level, under all that pressure, the ice crystals can slide past each other, grain by grain, slowly, so slowly. This is how a glacier is born, not in a moment, but across decades. Not by melting and freezing again, but by the patient, crushing weight of snow on snow on snow. And once a glacier exists, once it's thick enough and heavy enough, it begins to do something remarkable. It begins to move. The glacier flows downhill, pulled by gravity, shaped by the land beneath it, moving so slowly you'd never see it in a day or a week, or even a year, but moving nonetheless, reshaping itself, reshaping the land, all of this from snow, simple snow that refused to melt. Think about that for a moment. Something as light and delicate as a snowflake, given enough time and enough weight, becomes a force that can carve mountains, that can reshape continents, that can flow like a river made of stone. The transformation takes longer than a human lifetime, but it happens. It's happening right now on every glacier on Earth. Snow falling tonight in Alaska might become glacier ice when your great-grandchildren are old. Ice at the bottom of an Antarctic glacier might have started as snow when humans first built the pyramids. Glaciers are frozen time. Each layer is a year. Each bubble of trapped air is a breath of ancient atmosphere. Each crystal is a snowflake that never got to melt, pressed into something permanent and powerful. And here's the beautiful part. This entire process, snow to fern to ice to flowing glacier, follows simple rules. Weight presses down, crystals compress, ice flows under pressure. No magic, no mystery, just the physics of frozen water and the patience of time. You could understand every part of it. You could watch it happen if you had a few lifetimes to spare. But even knowing how it works doesn't make it less wonderful. A glacier is still a river of ice, miles long, moving while mountains stand still. Still ancient beyond human measure, still beautiful beyond words. So now we have ice. Deep, compressed, ancient ice. Layers stacked over centuries. Air bubbles trapped from atmospheres long gone. Crystals packed so tight they've become something new. But here's where it gets interesting. This ice doesn't just sit there. It doesn't wait patiently on the mountaintop or frozen plain. It moves. And as it moves, it does something extraordinary to everything in its path. So now we have ice. Deep, compressed, ancient ice. But here's where it gets interesting. Ice flows, not like water flows, much slower, but it flows nonetheless. A glacier in Alaska might move a few feet today. By tomorrow, a few more feet. In a year, maybe 100 feet downhill. Some glaciers move only inches per year. Others, the fast ones, might travel several feet per day. You'd never see it if you stood there watching. You could stare at a glacier for your entire lunch break and see nothing move. Come back next week, still looks the same. Come back next year. Maybe you'd notice a crack in a different place, a boulder that shifted position. But it is moving. Right now, this moment. Think of honey on a cold morning, thick, barely flowing. Tip the jar and the honey doesn't pour. It oozes, slow, patient, but definitely flowing. Glacier ice behaves the same way, not because it's melting, the ice stays frozen solid, but under its own enormous weight, under the pressure of hundreds of feet of ice stacked above, something strange happens. The ice becomes plastic. Not plastic like a bottle. Plastic meaning it can deform. It can change shape without breaking. The ice crystals at the bottom of the glacier, crushed by all that weight, starts to slide past each other, grain by grain, crystal by crystal. At the molecular level, bonds break and reform. Crystals slip. The ice flows like an incredibly thick fluid, even though it never stops being solid ice. It's called plastic deformation. The glacier is still frozen, still ice, but it behaves like a liquid in extreme slow motion. The bottom of the glacier flows faster than the top. The center flows faster than the edges. Just like a river, the sides drag against the rock walls of the valley. The bottom drags against the ground, but the middle, with less friction, moves faster. This creates stress inside the glacier. The ice pulls and pushes against itself. Sometimes, the stress becomes too much. The ice cracks. Deep crevasses open up, huge gaps that can be hundreds of feet deep, blue and dark and dangerous. But even as it cracks, it keeps flowing. The ice around the crevasse bends and moves. Eventually, the crack might close again, crushed shut by the flowing ice. Some glaciers flow around obstacles. A mountain in the way? The ice splits, flows around both sides, then joins back together on the other side. The ice remembers nothing about being separated. It just flows. Gravity pulls the glacier downhill, always downhill. The ice has no choice. It follows the path of least resistance, filling valleys, following the curves of the land. Where does it go? Depends on the glacier. Some flow down into warmer areas and melt, becoming rivers. Some reach the ocean and break apart into icebergs. Some flow into lakes. Some just get to a place where they melt as fast as they flow, and they stop there, in balance. But they never truly stop moving. Even a glacier that looks like it's staying the same size is flowing. Ice from the top is constantly moving down, replacing ice that melts at the bottom. It's flowing and melting at the same time, maintaining equilibrium. Right now, somewhere in Greenland, a glacier is sliding forward, a few inches today, tomorrow a few more inches, year after year, century after century. The ice that's at the front of the glacier today started as snow hundreds of years ago, miles back up the mountain. It's been flowing this whole time, slow, patient, unstoppable. And as this ice flows down the mountain, as it grinds against rock and soil, as it pushes forward with the weight of centuries behind it, it does something remarkable to everything in its path. It sculpts, it carves, it shapes the very bones of the earth. A glacier doesn't just flow over the land, it tears into it. As the ice moves, it picks up rocks, small pebbles, large boulders, even chunks as big as houses. These rocks get frozen into the bottom of the glacier, held tight in the ice. Now imagine what happens. The glacier flows forward, dragging these rocks across the ground beneath. It's like dragging sandpaper across wood, but the sandpaper is made of boulders, and the wood is solid bedrock. The rocks scrape, they gouge, they grind the stone beneath into powder. This powder is called glacial flour. It's so fine that when it washes into rivers and lakes, it turns the water a milky blue-green color. The color of glacier-fed water is unmistakable. But the glacier does more than grind. It plucks. As ice flows over bumpy bedrock, it freezes into cracks and crevices. Then, the glacier pulls forward, and chunks of rock come with it. Big pieces, sometimes the size of cars. The glacier literally rips the bedrock apart and carries it away. Year after year, century after century. The grinding and plucking never stops. This creates a very specific shape, a U-shaped valley, not the V shape that rivers carve. Glaciers don't work like that. A glacier fills the entire valley as it flows. It carves the bottom flat and the sides steep. When the glacier finally melts, it leaves behind a valley with a wide, flat floor and walls that rise straight up. Yosemite Valley in California looks like this. Those massive granite cliffs, carved by glaciers. The flat valley floor where people camp and hike, scraped smooth by ice. The fjords of Norway are the same. Deep valleys carved by glaciers, then filled with seawater when the ice melted. The water is dark and the cliffs rise straight from the surface. Glacier work. Glaciers also polish rock. Where the ice slides over stone, where the grinding is constant and even, the rock becomes smooth, almost shiny. You can run your hand over it and feel how smooth it is, even thousands of years after the glacier left. And they leave scratches, long, straight grooves, carved into bedrock by rocks, dragged along in the ice. Scientists call these glacial striations. They show which direction the glacier was moving. Some of these scratches are still visible millions of years after the ice melted. In places where glaciers once flowed, you can see their marks everywhere. Smooth bedrock, scratched surfaces, U-shaped valleys, piles of rock debris. The landscape has been completely reshaped. Mountains that once had sharp peaks got carved into pyramids with flat faces. Valleys that once meandered got straightened and deepened. Hills got scraped away entirely. A glacier is patient, but it's not gentle. It's one of the most powerful sculptors on Earth. And here's the thing. This is still happening. Glaciers in Alaska, in the Himalayas, in Patagonia, in Antarctica, they're carving right now. The rocks at their base are grinding. The bedrock is being scratched. The valleys are being deepened, slowly but constantly. If you've ever stood in a mountain valley and wondered why the walls are so steep and the bottom so flat, you might be standing in a glacier's artwork. If you've seen a massive boulder sitting alone in a field, far from any mountains, a glacier might have carried it there and left it behind when the ice melted. The landscape of entire continents has been shaped by ice, by glaciers that came and went over millions of years, each one leaving its mark. But glaciers don't just shape rock. They also create something delicate, something surprisingly beautiful. The ice itself, the ancient, compressed ice deep in a glacier, glows with a color that seems impossible. A blue so pure and deep it looks like it belongs in a dream. Deep glacier ice is blue, not reflected blue from the sky, not blue because of minerals. The ice itself glows blue. This happens because of how dense the ice becomes. Remember, glacier ice has been compressed for decades or centuries. The weight has squeezed out almost all the air. The crystals have grown large and packed tight. When light hits this dense ice, something specific happens. The ice absorbs red and yellow wavelengths. It drinks them in. But blue light, blue, bounces back out. So what you see is blue. Pure, deep blue. The denser the ice, the deeper the blue. Ice that's a few years old might look white or pale blue. Ice that's hundreds of years old glows with intense color. Some Antarctic ice is so old and compressed that the blue looks almost unreal, like looking into a frozen piece of sky. You can see this most clearly in crevasses. those deep cracks in the glacier. When you look down into them, the walls glow blue. The light filters through the ice, getting bluer and bluer the deeper it goes. Or in glacier caves. Sometimes meltwater carves tunnels through the ice. Walk into one of these caves and you're surrounded by blue light. The walls, the ceiling, everything glows. It's like being inside a sapphire. The blue is coolest in the shade. In direct sunlight, ice can look white because the surface reflects all the light. But in shadow, or deep inside the glacier, the blue emerges. Some glaciers have layers of different blues. Lighter bands where snow fell in heavy years. Darker bands where the ice is more compressed. The glacier becomes a striped record of time, written in shades of blue. And it's quiet in these blue spaces. The ice absorbs sound. Your voice doesn't echo the way it would in a rock cave. Everything feels muffled, hushed, like the ice is holding its breath. Photographers travel to glaciers just to capture this color. But photos never quite get it right. The blue is more intense in person, more luminous. It glows in a way that cameras can't fully capture. Scientists study the blue too. The exact shade can tell them about the ice density, about how much air is trapped inside, about how old the ice is. But you don't need to be a scientist to appreciate it. You just need to see it once. Stand at the edge of a crevasse and look down into blue that goes deeper than you can see. Or put your face close to old glacier ice and watch the light glow from within. It's the color of time made visible, of pressure and density and light behaving exactly as physics says it should. But knowing the science doesn't make it less beautiful. In Antarctica, there are blue ice areas where wind has scoured away the snow, exposing ancient ice. The ground itself is blue. You can walk across it, skate across it. The whole world turns blue. Some icebergs that break off glaciers are deep blue throughout. They've flipped over after calving, exposing ice that was deep in the glacier. These blue bergs drift through dark water like floating jewels. The blue tells you something important. This ice is old. It's been under pressure. It's been transformed from something light and airy into something dense and permanent. Every blue glacier carries this same color inside it, waiting. If you could cut one open like a cake, you'd see the blue running through it like veins. And inside this blue ice, trapped in those tiny air bubbles we talked about, something incredible is preserved. Not just air, not just atmosphere, but actual samples of the past, pieces of history frozen in time. Those air bubbles trapped in glacier ice aren't just empty space. They're samples of ancient atmosphere, tiny pockets of the past, sealed and preserved. When snow falls and gets buried, air gets trapped between the crystals. As the snow compresses into ice, some of that air gets squeezed out, but some gets sealed inside, locked in tiny bubbles, frozen in place. That air stays there for decades, centuries, in Antarctica for hundreds of thousands of years. Scientists drill into glaciers to extract these bubbles. They pull up long cylinders of ice called ice cores. Some of these cores are miles deep. Each layer represents 1 year of snowfall. They can count the layers, 1, 2, 3, like counting tree rings. But instead of rings, it's bands of ice. Light layers from summer, darker layers from winter, year after year, stacked on top of each other. The deepest ice cores go back 800,000 years, nearly 1 million years of Earth's atmosphere, preserved in ice. When scientists extract the air from these bubbles, they can analyze it, measure the carbon dioxide, the methane, the oxygen levels. They can tell what the atmosphere was like when that snow fell. This is how we know about past climates. The ice remembers. It holds evidence of ice ages and warm periods, of volcanic eruptions that filled the air with ash, of changes that happened long before humans existed. A bubble in Antarctic ice might contain air from when your ancestors first learned to control fire, from when mammoths walked the earth, from before modern humans even existed. The air is still fresh, still sealed. Open the bubble, and that ancient air mixes with today's air. The past meets the present in a single breath. But it's not just air that gets trapped. Pollen gets buried in the snow, dust, volcanic ash, tiny particles that tell stories about what was happening on Earth's surface. Scientists found volcanic ash in ice cores and matched it to specific eruptions. They found pollen and figured out what plants were growing. They found dust from deserts blown across oceans and frozen into glaciers thousands of miles away. Every layer is a snapshot, a frozen moment. The ice doesn't forget. It doesn't decay. It just waits, holding its secrets. In Greenland, scientists drilled through the entire ice sheet, more than 2 miles of ice. At the bottom, they found ice from 130,000 years ago, the last warm period before our current one. The air in those bubbles is from a completely different world. The ice cores also show us how quickly climate can change. The layers reveal warm periods that lasted thousands of years, then sudden shifts to cold. Changes that happened in decades, not centuries. The ice shows us Earth's climate is not stable. It moves, it shifts, it changes. And we can see it all because snow kept falling year after year, building up, trapping time. Think about it. Snow that fell when Rome was an empire is still frozen in a glacier somewhere. Air from the Middle Ages sits in bubbles in Antarctic ice. The atmosphere your great-great-great-grandparents breathed is preserved in Greenland. Glaciers are time machines, not for traveling through time, but for retrieving it, for bringing the past back to us, one ice core at a time. Right now, scientists are drilling new cores, searching for older ice, trying to go back further, to find ice from 1 million years ago, 2 million, to see what Earth's atmosphere was like even deeper in time. The ice holds answers about our past, about how climate works, about how quickly things can change. But these glaciers that preserve time are also changing themselves, growing and shrinking with Earth's rhythms, advancing in cold periods, retreating when it warms. The Earth breathes, and the glaciers show us how. Glaciers grow, they shrink, they advance down valleys, they retreat back up mountains. Earth breathes through its ice. When the climate cools, more snow falls, less melts. Glaciers thicken, they push forward, covering more land. Mountains that were bare get buried under ice. Valleys fill up. When the climate warms, less snow falls, more ice melts. The glaciers thin, they pull back. Land that was frozen for thousands of years sees sunlight again. This has happened over and over throughout Earth's history. The last major ice age peaked about 20,000 years ago. Back then, glaciers covered huge portions of the northern continents. Ice sheets stretched from the Arctic down to where New York City is now. Chicago was under 1 mile of ice. So was most of Canada. In Europe, ice covered Scandinavia and pushed down into Germany. The weight was so enormous that it actually pressed the land down. The continents sagged under the ice. The glaciers carved the Great Lakes, scraped out thousands of smaller lakes, flattened hills, created new valleys, changed the path of rivers. Then, about 15,000 years ago, the world started warming. The ice began to melt, slowly at first, then faster. The glaciers retreated, not all at once. They'd pull back for a while, then pause. Sometimes they'd advance again briefly, but overall they shrank. Water from the melting ice flooded into the oceans. Sea levels rose, hundreds of feet. Land bridges that connected continents disappeared underwater. Britain became an island. Asia and North America separated. The land that had been pressed down started to rise again. It's still rising today in some places. Scandinavia lifts a few millimeters each year, still rebounding from the weight of ice that melted thousands of years ago. By 10,000 years ago, most of the big ice sheets were gone. Only Antarctica and Greenland still held massive amounts of ice, and smaller glaciers in high mountains. But this wasn't the first time this happened. Earth has gone through many ice ages. The continents have been frozen and thawed over and over. We're still technically in an ice age now, just a warm part of it. Scientists call this an interglacial period, a pause between glaciations. The ice hasn't disappeared completely. It's just waiting. In the past, these warm periods lasted about 10,000 years. Then the climate cooled again. The glaciers returned. Ice crept back down from the poles. Forests became tundra. The Ice Age resumed. We're about 10,000 years into our current warm period. But here's the thing. The pattern might be changing. Human activity is warming the planet faster than natural cycles would. The glaciers that would normally be stable, or maybe even growing slightly, are shrinking instead. This isn't speculation. We can measure it. Photos from 50 years ago show glaciers much larger. Photos from 100 years ago show them even bigger. Some glaciers have lost half their mass in a single human lifetime. Small glaciers have disappeared completely. Mountains that had ice for thousands of years are now bare rock. The breathing has changed rhythm. Earth is exhaling ice faster than it's inhaling snow. In the Alps, glaciers that people skied on in the 1980s are now just patches of ice clinging to peaks. In Glacier National Park, there were 150 glaciers in 1850. Now, there are about 25. The evidence is visual, direct. You can see it in before and after photos. The ice is retreating. This matters because glaciers feed rivers. Millions of people depend on glacier meltwater for drinking water and crops. As the glaciers shrink, those rivers will change. Some might run dry in summer. The ice remembers every warm period and every cold period Earth has ever had. It shows us that climate changes, always has. But the current change is happening faster than most of the natural changes preserved in the ice. And yet, even as they melt, glaciers continue to hold mysteries, continue to harbour life in places you wouldn't expect. Life exists in glaciers, not just near them, not just on their edges, inside them, on them, in the ice itself. There are worms that live their entire lives in glacier ice. Ice worms. They're small, thin, dark-coloured, and they only exist at one temperature, right around freezing. Too cold, they die. Too warm, they die. They live in the narrow zone where ice is just starting to melt, where tiny water films form between ice crystals. They eat algae and bacteria. They move through the ice by squeezing between crystals. At night, they come to the surface. During the day, when the sun heats the ice, they burrow deeper to stay cool. These worms have antifreeze proteins in their bodies. Literally, their cells produce chemicals that prevent ice from forming inside them. Without these proteins, they'd freeze solid. They're found in glaciers from Alaska to Washington state. Millions of them, writhing through the ice, invisible unless you look closely. Then there are the algae, snow algae. They grow on glacier surfaces and turn the ice pink or red, sometimes green. The pink ones are called watermelon snow. Step on it and it actually smells sweet, like watermelon. The algae produces this scent as a byproduct of its metabolism. These algae have adapted to intense cold and brutal UV radiation. The pigments that make them red or pink act as sunscreen, protecting them from radiation that would kill most life. They bloom in summer when meltwater appears. The whole surface of a glacier can turn pink with algae. Then winter comes and they go dormant, frozen but not dead, waiting for the next thaw. Bacteria live in glaciers too, deep inside where it's always dark and frozen. They survive by metabolizing minerals in the rock dust trapped in the ice. They live so slowly that a single generation might take years. Some of these bacteria have been frozen for thousands of years. Scientists revive them in labs. The bacteria wake up and start growing as if no time passed at all. Glacier mice are another strange form of life. Not actual mice. They're balls of moss that form on some glaciers. They roll around slowly on the ice surface, moved by wind and meltwater. The moss grows on all sides because the balls keep rolling, so every side gets sunlight. They move together in herds. Scientists tracked them and found they travel about an inch per day, all moving in roughly the same direction. No one knows why. Tardigrades live on glaciers too. Water bears, microscopic animals that can survive almost anything. Freeze them, they survive. Dry them out, they survive. Shoot them into space, they survive. On glaciers, they live in the thin water films around ice crystals, eating bacteria and algae, tiny and indestructible. Birds nest near glaciers. Seals rest on glacier ice, floating in the ocean. Fish spawn in glacier-fed streams, drawn by the cold, mineral-rich water. Even insects have been found living in glacier ice. Springtails, ice crawlers, tiny creatures that have adapted to permanent cold. Life doesn't just tolerate glaciers. Some species need them. They've evolved specifically for ice environments. These creatures exist nowhere else. This matters because as glaciers shrink, these species lose their habitat. Iceworms have nowhere to go when their glacier melts. Snow algae can't migrate to a cooler place. They're stuck. Glacier mice dry out and die when the ice disappears. The bacteria go dormant or get washed away. The ecosystem collapses. But for now, right now, life persists in the ice, thriving in conditions that seem impossible, finding ways to exist in a world of cold and blue and endless patience. And these tiny creatures are part of something larger, part of an ecosystem that depends on glacier water flowing down mountains, feeding into streams and rivers. Water from glaciers feeds rivers that millions depend on. Every day, glaciers melt, not dramatically, just steady dripping. Water trickling from the ice, collecting in small streams. Those streams merge. They become rivers. These rivers have a specific color, milky blue-green or gray. That's the glacial flower we talked about. Rock ground so fine it stays suspended in the water. The particles are too small to settle. They float, turning the water opaque. Hold a glass of glacier water up to light, and you can't see through it. But let it sit for hours, and the particles slowly settle. The water clears. At the bottom of the glass, a film of grey dust. This water is cold, just above freezing, even in summer. Fish that live in glacier-fed rivers have adapted to extreme cold. Their blood contains antifreeze compounds, just like the ice worms. The water is also clean, filtered through ice. No pollutants from upstream, because there is no upstream. The glacier is the source. The water comes from snow that fell years ago, melted today, now flowing to the sea. In the Andes, entire cities depend on glacier meltwater. Lima, Peru, gets most of its water from glaciers high in the mountains. When the glaciers melt in summer, they release water. The rivers swell. The reservoirs fill. In the Himalayas, the Ganges and Indus rivers are fed partly by glaciers. Hundreds of millions of people use that water for drinking, for crops, for everything. The timing matters. Glaciers store water as ice in winter. They release it in summer when rainfall is low and crops need watering. Natural reservoirs, natural timing. But as glaciers shrink, this timing changes. In the short term, more water flows. The extra melting means fuller rivers. But eventually, the glacier gets too small. It can't store enough water. Summer rivers start running dry when they're needed most. Some rivers have already changed. Rivers that once flowed strong in July now barely trickle. Farmers notice. Cities notice. The water also provides power. Hydroelectric dams in Norway, Canada, New Zealand. Many are fed by glacier meltwater. Steady flow, predictable timing, but only as long as the glaciers persist and the water carries nutrients. That glacial flour isn't just rock dust, it's minerals, iron, calcium, phosphorus. These minerals fertilize the ocean when rivers reach the coast. Plankton blooms where glacier rivers meet the sea. The minerals feed the plankton. The plankton feed small fish. The small fish feed larger fish. The whole food web starts with rock dust from glaciers. Salmon spawn in glacier-fed streams. They prefer the cold, clear water, the gravel beds carved by ancient glaciers. They swim upstream to lay eggs in the exact places glaciers created. In Alaska, bears gather at rivers to catch salmon. The salmon are there because of glacier water. The bears are there because of the salmon. Remove the glacier and the entire system shifts. Some glaciers create outburst floods. Water builds up inside or beneath the ice. Pressure grows. Eventually, the ice dam breaks. Millions of gallons rush out all at once. These floods can be enormous. Bridges get swept away. Valleys flood. Then, just as quickly, the water is gone. The river returns to normal, until it happens again next year. In Iceland, they have a word for this. Jökullaup. Glacier burst. It's a known danger, part of living near ice. The water from glaciers shapes everything downstream. The chemistry of rivers, the species that live in them, the people who depend on them, the land the water flows across. Right now, somewhere, glacier meltwater is flowing, carrying rock dust, feeding a river, traveling from ice to ocean, and along the way it leaves gifts, creates landscapes, fills lakes in places glaciers carved thousands of years ago. When glaciers retreat, they leave holes in the ground, deep basins carved into bedrock, and these holes fill with water. This is how most of the world's lakes formed. The Great Lakes, the largest group of freshwater lakes on Earth. All 5 were carved by glaciers. As the ice pushed south, it dug deep troughs in the soft bedrock. When the ice melted, water filled those troughs. Lake Superior is over 1,300 feet deep in places. The glacier that carved it scraped away that much rock, then disappeared, leaving behind enough water to cover North and South America in a foot of water. Thousands of smaller lakes dot Canada, Scandinavia, and the northern United States. Drive through Minnesota and you'll see lake after lake. Wisconsin, Michigan, Ontario, all glacier work. The lakes have a specific shape, long and narrow, usually, following the path the glacier took. Some are circular, where the ice carved a bowl. Others are irregular, where the glacier melted unevenly and left pockets. Many glacial lakes are deep, deeper than rivers could ever carve. The ice didn't just erode the surface, it gouged down into bedrock. Some lakes have bottoms hundreds of feet below sea level, even though the lake surface is high in the mountains. The water in these lakes is often clear. No sediment flowing in from upstream because glaciers tend to carve lakes at the head of valleys. The water comes from rain, from snowmelt, from springs. It has nowhere else to come from. Some glacial lakes are bright blue or green. The rock flour from nearby glaciers washes in and suspends in the water. Lake Louise in Canada, Peyto Lake, lakes that look fake in photos because the colour is so intense. In New Zealand, glacial lakes reflect the Southern Alps. The water is so still on calm days that you can't tell where the mountains end and their reflection begins. Sky, mountain and lake become one image. Finland has 188,000 lakes, most of them glacial. The entire landscape is a maze of water and land. The ice sheet that covered Scandinavia scraped and gouged and left behind this intricate pattern. Some glacial lakes are temporary. They form behind ice dams. Water collects behind a glacier or a ridge of glacial debris. The lake grows. Then the dam breaks or the ice melts and the lake drains, sometimes catastrophically. In Iceland, glacial lakes form and drain regularly. A lake will appear one summer, grow for months, then vanish overnight when the ice dam fails. The valley fills with rushing water and icebergs. Then it's empty again. Other glacial lakes last thousands of years, long enough to develop their own ecosystems. Fish colonize them, plants grow along the shores, birds nest. The lake becomes permanent. Glacial lakes also act as sensors. Their levels rise and fall with glacier health. A shrinking glacier means less meltwater. Lake levels drop. Entire lakes have disappeared as their glacier source vanished. Some lakes are still forming right now. As glaciers retreat, they reveal new basins. Water collects. Within years, a new lake exists where ice once sat. These lakes are bare at first. No plants, no fish, just water and rock. But life arrives. Seeds blow in. Birds bring fish eggs on their feet. Within decades, the lake looks like it's always been there. Glacial lakes are freshwater reservoirs. They hold water that fell as snow decades or centuries ago. Now it sits, calm and still, waiting to flow downstream, waiting to evaporate and become clouds, waiting to continue the water cycle. Stand at the edge of a glacial lake and you're looking at a glacier's footprint, the exact shape of ice that's no longer there. The water remembers. It fills the space perfectly, showing you where the glacier carved deepest. But some lakes exist in even stranger places, not where glaciers were, but where they still are, hidden beneath miles of ice in complete darkness. Beneath some glaciers, there are lakes, hidden under miles of ice, sealed away from sunlight, from air, from everything. Lake Vostok in Antarctica is the size of Lake Ontario. It sits under more than 2 miles of ice. The ice above it is so heavy that the pressure keeps the water liquid, even though it's far below freezing. Scientists discovered it using radar. They sent radio waves through the ice. The waves bounced back differently when they hit water instead of rock. That's how they knew something was down there. The lake has been sealed for at least 15 million years, maybe longer. Nothing from the surface has reached it in all that time. No light, no fresh air, no new organisms. But there might be life in it. Heat from Earth's core warms the bottom of the lake. The water stays liquid, around 27 degrees Fahrenheit, below freezing, but liquid because of the pressure. And where there's liquid water and energy, life finds a way. Scientists desperately want to drill down and sample the water, but they have to be careful. If they contaminate the lake with surface bacteria or chemicals from the drill, they'll destroy what they came to study. So they wait, they plan, they develop clean drilling methods. Other subglacial lakes exist, hundreds of them under Antarctica. Some are connected by rivers that flow beneath the ice. Water moves in darkness from lake to lake, carrying whatever might live there. These lakes fill and drain in cycles. The ice above shifts. Pressure changes. Water flows from one lake to another. Scientists watch the surface of the ice rise and fall as lakes beneath fill and empty. In Greenland, there are subglacial lakes too, smaller than Antarctica's, but still hidden, still isolated, still mysterious. What could live in these lakes? Bacteria, probably. Organisms that survive on chemicals and heat instead of sunlight. Similar to life found in deep ocean vents. Species that evolved in total isolation, cut off from the rest of Earth's biosphere. Some scientists think these lakes might be similar to oceans on other worlds. Europa, Jupiter's moon, has an ocean under ice. Enceladus, Saturn's moon, has liquid water beneath its surface. If life can exist in Earth's subglacial lakes, maybe it can exist there too. The water in these lakes is ancient. It's been cut off from the atmosphere for millions of years. The chemistry is different. The dissolved gases, the minerals, everything about it is from a different time. Ice cores drilled near Lake Vostok show that the lake water sometimes freezes onto the bottom of the glacier. This ice is different from regular glacier ice. It formed from liquid water, not from compressed snow. Scientists can identify it and study it without drilling all the way down. That ice contains clues, bubbles of lake water, possibly frozen bacteria, evidence of what's down there without actually reaching the lake itself. The pressure at the bottom of these lakes is immense, the weight of 2 miles of ice pressing down. Anything living there has adapted to crushing pressure, to eternal darkness, to isolation. Some of these lakes are the most remote, untouched places on Earth, more isolated than the deepest ocean, more cut off than the highest mountain. They're completely sealed worlds beneath the ice. And they're not static. They're part of the glacier system. As the ice moves, it affects the lakes. As the lakes fill and drain, they affect how the ice flows above them. Everything connects, even in darkness. Right now, while you lie here, Lake Vostok sits in absolute silence. No wind, no waves, just still water under crushing pressure, waiting, holding whatever secrets it's held for millions of years. And above these hidden lakes, where glaciers meet the ocean, something dramatic happens. The ice breaks, it carves, it creates floating mountains that drift into the sea. Some glaciers don't stop at the shore. They keep flowing right into the ocean. The front edge of the glacier floats. Ice is less dense than water, so it rises. But it's still connected to the glacier behind it, still being pushed forward by all that ice flowing from the mountains. Eventually, the stress becomes too much. The ice cracks. A piece breaks off. This is calving. The moment a glacier gives birth to an iceberg, the sound is like thunder, a deep crack that echoes across the water. Then, a tremendous splash as thousands of tons of ice hit the ocean. Waves radiate outward. The water churns white. Sometimes the carving is small. A chunk the size of a car breaks off. Sometimes it's massive, a piece as large as a building, or several buildings, or an entire city block. In 2017, an iceberg broke off from Antarctica that was larger than Delaware. One single piece of ice. It drifted away slowly, a floating island. Not all icebergs are white. Some are striped with blue, where dense ice is exposed. Some have dirt and rocks frozen inside them. Debris the glacier picked up decades ago, now trapped in ice, floating at sea. The shape of an iceberg depends on how it broke and how it floats. Flat ones are called tabular. They look like floating tables. Others are jagged with spires and peaks. Some are rounded and smooth. And here's the famous part. Most of the iceberg is underwater. Ice floats, but just barely. About 90% sits below the surface. What you see above the water is just the tip. The bulk of the iceberg is hidden beneath, massive and invisible. This makes them dangerous for ships. The Titanic hit an iceberg. The part below the waterline tore open the hull. The ship sank because of ice it never saw. Icebergs drift with ocean currents. Some travel thousands of miles from where they carved. Antarctic icebergs drift north into warmer water. Greenland icebergs float south into the Atlantic shipping lanes. As they drift, they melt. The warm ocean water eats away at them from below. The sun melts the top. Waves carve caves and arches. The iceberg changes shape constantly. Some icebergs flip. As the bottom melts faster than the top, the center of gravity shifts. The berg becomes unstable. It rolls over. What was underwater is now exposed to air. Deep blue ice that hasn't seen daylight in centuries. These flipped bergs are intensely blue. The compressed ice that was deep in the glacier now forms the surface. Photographers chase these blue bergs, trying to capture the color before the berg melts or flips again. Icebergs can last months or even years, slowly shrinking, slowly melting, releasing fresh water into the ocean. That water is ancient, frozen decades or centuries ago, now becoming part of the sea again. Animals use icebergs. Seals rest on them. Penguins hop onto them for safety from predators in the water. Birds land on them. They're floating islands of ice in the middle of the ocean. As icebergs melt, they release bubbles, ancient air escaping. The ice cracks and pops. If you're close enough, you can hear it, a constant fizzing sound, the iceberg singing as it dies. Eventually, every iceberg melts completely. The ice returns to water. The journey from snow to glacier to iceberg to ocean is complete. The cycle closes. But before they vanish, icebergs are beautiful, white and blue against dark water, floating sculptures carved by chance, each one unique, each one temporary. Right now, somewhere in the Arctic or Antarctic, an iceberg is drifting, melting slowly, changing shape, making its way through cold water toward warmer seas where it will finally disappear. And as these icebergs melt and die, they make sounds. But glaciers make sounds too. Strange sounds. The voice of ice itself, speaking in groans and whispers. Glaciers are never silent. They groan, they crack, they rumble deep inside. The ice is always moving, always under stress. As it flows, different parts move at different speeds. Internal pressure builds. The ice strains against itself. Then it releases. A crack forms. The sound travels through the ice for miles. Deep, resonant. like the earth itself is sighing. Sometimes the sounds are high-pitched, squeals and squeaks when ice crystals scrape past each other under pressure. Sometimes they're low, rumbles that you feel in your chest more than hear. Scientists record these sounds. They place sensors on glaciers and listen. Each glacier has its own voice, its own pattern of sounds. Some glaciers sound like whales singing, long, mournful calls that echo through the ice. Others sound like wind howling through caves, or like distant thunder that never quite arrives. The sounds tell stories. A loud crack means a crevasse just opened. A low rumble means the glacier is settling, adjusting to its own weight. High-frequency pings mean ice is fracturing at a microscopic level. In summer, glaciers are louder. More meltwater flows through them. The water carves channels inside the ice. It rushes through tunnels and drops into moulins, deep vertical shafts where surface water plunges into the glacier's interior. The water sounds echo through the ice, rushing, falling, creating a constant background of liquid sound inside the solid glacier. At night, when the temperature drops, the ice contracts. This creates new stresses, new cracks. Some glaciers are noisiest in the early morning, when the night's cooling has created the most strain. Calving glaciers are the loudest. When a massive chunk of ice breaks off and crashes into water, the sound can be heard for miles. First the crack, then the splash, then the rumble of displaced water and shifting ice. Even small movements make sound. The glacier settling, ice crystals realigning, tiny adjustments that accumulate into audible groans. People who live near glaciers get used to these sounds. They know what a normal crack sounds like versus a dangerous one. They can hear when the glacier is particularly active. Mountaineers sleeping on glaciers hear the ice talking all night. Creaks and groans beneath their tents. Reminders that they're sleeping on something alive, something moving. The sounds travel differently through ice than through air. Ice conducts sound waves efficiently. A crack that happens a mile away can sound like it's right next to you. The ice transmits it, focused and clear. Some of the sounds are ultrasonic, too high-pitched for humans to hear, but they're there, vibrating through the ice. Bats could probably hear them, or dolphins if they were somehow on a glacier. Recording equipment picks up these ultrasonic sounds. When scientists slow them down, they become audible. The glacier suddenly has an entirely different voice, a secret language it was speaking all along. The ice also amplifies certain frequencies, resonates with them, like a musical instrument. The glacier becomes a giant resonator, turning small vibrations into louder sounds. In Antarctica, some research stations are built on ice shelves. The people inside can hear the ice constantly. It's part of their daily life. The shelf groaning, adjusting, speaking. They say you get used to it, but you never quite forget that you're living on floating ice, that beneath you, the ice is moving, cracking, singing its deep songs. Pour glacier ice into water and you hear something different. Tiny pops and crackles, air bubbles escaping, air that's been trapped for hundreds or thousands of years, finally released. It sounds like static, like distant fireworks, like stars would sound if stars made noise. Each pop is ancient atmosphere meeting the present. And all these sounds, the groans, the cracks, the pops, they're the voice of time. Ice that formed slowly, now changing, moving, eventually melting, and speaking as it goes. Humans have always been drawn to glaciers, fascinated, sometimes afraid, always in awe. Ancient people carved images near glaciers, handprints on rocks, Animal figures, symbols whose meanings are lost. They stood at the edge of the ice and left their mark. Some cultures considered glaciers sacred. The ice was a dwelling place for spirits. Mountains topped with glaciers were too holy to climb. Water from glaciers was used in ceremonies. In 1991, hikers in the Alps found a body emerging from a melting glacier. Ötzi, the Iceman. He'd been frozen for over 5,000 years, perfectly preserved. He died on a mountain pass, and the ice claimed him. For 5 millennia, he lay there, while empires rose and fell. While humans invented writing, built cities, went to war, made peace. And Ötzi stayed frozen. The ice preserved his skin, his clothes, his tools, even the contents of his stomach. Scientists could tell what he ate for his last meal, could see the tattoos on his body, could analyze his DNA. He was carried by the glacier, slowly, downhill, moving inches per year, until finally, in our warming world, the ice melted enough to expose him. And we found him, a messenger from the distant past. Glaciers have preserved other things too. Woolly mammoths in Siberia, ancient forests crushed and frozen, objects dropped by travelers centuries ago, now emerging as the ice retreats. Mountain guides have worked with glaciers for hundreds of years, learning their moods, their dangers, which crevasses to avoid, which routes to take. In the Alps, guides mark safe paths across glaciers with flags and ropes. These routes change every year as the ice shifts. What was safe last summer might be a gaping crevasse this summer. Climbers rope themselves together when crossing glaciers. If one person falls into a hidden crevasse, the others can catch them, hold them, pull them out. The glacier doesn't care. It just waits, patient and cold. Some people drink glacier water, claiming it's the purest water on Earth. And in some ways, it is. Frozen before pollution, before industry, ancient precipitation now melted. But glacier ice can also contain volcanic ash, dust from ancient deserts, even traces of metal. The ice captures whatever was in the atmosphere when the snow fell. It's a record, not always pure. Tourists visit glaciers by the millions. They walk on the ice wearing crampons, ride boats between icebergs, stand at viewpoints photographing the blue. Iceland built an entire tourism industry around glaciers. Guided walks, ice caves, glacier lagoons where seals swim between floating ice chunks. The glaciers there have names, personalities. Some glaciers are named after people. Perito Moreno in Argentina, named after an explorer. It's one of the few glaciers still advancing, pushing forward, blocking a lake until the ice dam bursts every few years in a spectacular flood. Others are named for what they look like or where they are. Fox Glacier, Franz Josef. Simple names for enormous rivers of ice. In Glacier National Park, they've been photographing the same glaciers since the 1800s. The same locations, the same angles. The comparison is stark. The ice has retreated dramatically. Some glaciers have disappeared entirely. These photos are archives, evidence. The glaciers are telling us something, showing us change in the most visible way possible. Scientists camp on glaciers for months, drilling, measuring, recording, living in tents on moving ice, doing work that helps us understand climate, history, the future, and all of this, the ancient bodies, the tourism, the science, the guides, the sacred sites, all of it connects back to the same thing. Ice, patient ice that flows and carves and preserves and speaks. Right now, while you rest here, someone is standing on a glacier, feeling small, feeling the cold wind, looking at ice that's older than their country, than their language, than most of human civilization. Not all glaciers are the same. Some behave strangely. Some exist in places you wouldn't expect. Rock glaciers look like rivers of stone, but beneath the rocks, ice holds everything together. The rocks insulate the ice, protecting it from melting. The whole mass flows downhill like a normal glacier, but from above, you'd see only boulders. These exist in places too warm for regular glaciers. The rock layer acts as a shield. Underneath, ice persists, flows. Does its glacier work invisibly? Debris-covered glaciers are similar but different. A layer of rock and dirt covers the ice, sometimes feet thick. The glacier becomes camouflaged. You could hike across one without knowing you're walking on ice. In the Himalayas, many glaciers are debris-covered. Centuries of rockfall from surrounding peaks have buried them. The ice still flows underneath, still carves the valley, but it's hidden, secret. Surge glaciers are the strange ones. Most glaciers move steadily. Surge glaciers don't. They stay mostly still for years or decades, barely moving. Then suddenly they surge. The ice accelerates. Instead of feet per year, suddenly it's feet per day, or per hour. The glacier races forward, sometimes advancing miles in a single season. Then it stops, goes back to sleep, waits another few decades before surging again. Scientists aren't entirely sure why this happens. Something about water buildup at the base, about pressure, about the glacier reaching some threshold where it has to move fast. Hubbard Glacier in Alaska surges. When it does, it can block a bay, trapping seals and fish behind an ice dam. Then the surge ends. The ice slowly retreats. The bay opens again. Hanging glaciers cling to cliff faces. They're stuck to steep rock, defying gravity. Too small to flow down like normal glaciers. Too stubborn to fall off. But sometimes they do fall. The ice breaks away and avalanches down the mountain. Thousands of tons tumbling, creating enormous clouds of ice and snow. Tidewater glaciers flow directly into the sea. We talked about these, but some of them do something unexpected. They float for miles before breaking up. The tongue of the glacier extends into the ocean, a highway of ice over water. Ships sometimes sail alongside these floating extensions. The glacier towers above them, blue ice rising from the sea, still connected to land miles away. Tropical glaciers exist near the equator, high on mountains in Peru, in Ecuador, in Indonesia. The altitude is so great that despite the tropical location, snow falls and doesn't melt. These glaciers are small, fragile, shrinking fast, but they exist. Ice within view of rainforests. The glaciers on Kilimanjaro are disappearing. Photos from 100 years ago show the summit covered in white. Now, just patches remain. Soon, maybe none. In Iceland, glaciers sit on top of volcanoes. The ice covers active volcanic systems. Heat from below, ice above. When the volcano erupts, it melts the glacier from underneath. Water and ice and lava mix. The result is a glacial flood filled with ice chunks and volcanic debris. The Icelandic word, jökulhlaup, means exactly this. Glacier burst caused by volcanic heat. Some glaciers in Antarctica are being melted from below by warm ocean currents. The ice shelf floats. Warm water circulates underneath. The glacier thins from the bottom up. Eventually, it breaks apart into icebergs without ever melting at the surface. There are glaciers in caves, ice caves where the temperature stays below freezing year-round. The ice builds up inside the cave, creating formations like stalactites, but made of ice instead of stone. And there are glaciers so remote that humans have never walked on them. Glaciers in Antarctica. that have no names. No visitors, just ice flowing in absolute solitude. Every glacier has its own character, its own way of existing, some conventional, some bizarre. All of them ice, all of them flowing, all of them part of Earth's frozen archive. Earth wasn't always like this. There were times when glaciers covered almost everything. Scientists call it Snowball Earth, a period when ice stretched from pole to pole, when glaciers reached the equator, when the entire planet froze. This happened more than once. The most severe was about 650 million years ago. Ice covered the oceans. Snow covered the land. The whole world turned white. Imagine looking at Earth from space during Snowball Earth. No blue, no green, just white ice, and maybe some dark volcanic peaks poking through. How did life survive? That's the question scientists asked. Some think life persisted near volcanic vents, hotspots where the ice was thin or absent, pockets of warmth where organisms could survive. Others think the ocean under the ice wasn't completely frozen. That liquid water existed beneath, dark and cold, but liquid. Life could have survived there. The ice was miles thick in places, thicker than any glacier today. The weight pressed down on the continents. Everything was buried. What ended Snowball Earth? Volcanoes. Even covered in ice, Earth's volcanoes kept erupting. They released carbon dioxide into the atmosphere. Normally, this CO2 gets absorbed by oceans and weathered rocks. But with everything frozen, the CO2 just accumulated. For millions of years, it built up. The atmosphere got thicker with greenhouse gas. The temperature slowly rose. Eventually, it got warm enough for ice to start melting. Once it started, it accelerated. Ice reflects sunlight. Water and land absorb it. As ice melted, more heat got absorbed. More ice melted. Feedback. The thaw might have been relatively quick. A few thousand years. Snowball Earth became Ocean Earth. The glaciers retreated to the poles. Life exploded in diversity. The world bloomed. This wasn't the only deep freeze. Earth has gone through multiple snowball or near snowball periods. Each time, life survived somehow. Each time, the ice eventually retreated. Between these extreme ice ages, there were countless smaller glaciations. Ice ages that covered continents, but not everything. The cycle of freeze and thaw has been Earth's pattern for billions of years. During the Permian period, about 300 million years ago, glaciers covered much of the southern hemisphere. Antarctica, Australia, South America, Africa, they were all connected then, forming one supercontinent. Glaciers flowed across it. Evidence remains. Glacial scratches in South African rocks. Glacial deposits in Australia. The same patterns we see from ice ages today, but from hundreds of millions of years ago. The dinosaurs never saw massive glaciers. During their time, Earth was warm. No polar ice caps. Forests grew in Antarctica. Crocodiles swam near the Arctic. Then the dinosaurs disappeared. Mammals rose, and the world began cooling again. The current ice age started about 2.6 million years ago. We're still in it. The ice hasn't left completely. Antarctica and Greenland remain frozen. Mountain glaciers persist. This is an ice age, just a warm phase of one. Our ancestors evolved during this ice age. Early humans walked across land bridges exposed by low sea levels. They hunted mammoths in cold grasslands at the edge of ice sheets. We're children of the Ice Age. Our species was shaped by advancing and retreating glaciers, by cold periods and warm, by changing climates and shifting landscapes. And now we're living in what might be the end of this Ice Age. or the beginning of something different. The glaciers are retreating faster than they have in thousands of years. Whether the ice will return or disappear completely, we don't know. Earth's climate has always changed, always cycled. But now, for the first time, a species is influencing that cycle. The glaciers remember everything. They hold the record in their ice. They show us the patterns, the rhythms, the long, slow dance of freeze and thaw that has shaped our planet. And they're still here, still flowing, still carving, still holding on to winter, even as the world warms around them. Scientists can read glaciers like books. Each layer tells a story. Each bubble holds evidence. The ice remembers everything. Ice cores are the key. Long cylinders drilled from deep within glaciers. Some reach down 2 miles. Each inch of core represents time, years stacked on years. The layers are visible. Light bands from summer when more snow fell. Dark bands from winter. Count them like tree rings. 1 year, 2 years, 10,000 years. Down and down into the past. But it's not just about counting. The ice reveals chemistry, climate, atmosphere. Oxygen isotopes in the ice show temperature. Heavy oxygen versus light oxygen. The ratio changes with temperature. Scientists measure this and reconstruct ancient climates with precision. They can tell when it was warm, when it was cold, how much warmer, how much colder. The ice doesn't guess, it records. Dust in the ice shows wind patterns. When the climate was dry, more dust blew around. More got trapped in snow. Layers with heavy dust mark drought periods. Clean layers mark wetter times. Volcanic eruptions show up clearly. A layer of ash. Sometimes thick, sometimes just a trace. But it's there, marking the exact year a volcano erupted. Scientists can match these ash layers to known eruptions, date the ice precisely. The deepest ice cores go back 800,000 years. But scientists want older ice. They're searching for ice from 1 million years ago. 2 million. Ice that remembers even deeper time. In Antarctica, there are places where ice flows slowly, where layers don't get disturbed. These are the best places to drill. The ice stays organized. The oldest layers at the bottom, the newest at the top. Each core is precious. Scientists store them in freezers, study them for decades, share samples with researchers around the world. The ice continues teaching long after it's been drilled. Some cores show rapid climate shifts, warm periods that lasted only decades before plunging back into cold. Changes so fast that ecosystems couldn't adapt. Species went extinct. Others migrated or evolved quickly. The ice shows that Earth's climate isn't stable. It shifts, sometimes gradually over thousands of years, sometimes shockingly fast. Pollen grains trapped in ice reveal what plants were growing, what the landscape looked like, when forests advanced and retreated, when tundra replaced trees. Even tiny particles of soot show up, evidence of forest fires, of volcanic activity, of meteor impacts that filled the atmosphere with debris. Methane trapped in bubbles tells another story. Methane comes from wetlands, from decomposing organic matter. High methane means more wetlands, more life, a wetter, warmer world. Lead appears in recent ice layers, evidence of human activity. Ancient Romans, smelting silver, released lead into the atmosphere. It travelled around the world and fell with snow. Now it's in the ice, proof of civilization thousands of miles away. Modern ice shows even more human fingerprints. Radioactive isotopes from nuclear tests, pollutants from industry, plastic particles. The ice documents our impact, but most of the ice is pure, clean, a record of Earth before humans, before cities, before agriculture. A baseline showing what the planet was like when only natural forces shaped climate. Scientists compare ice cores from different glaciers, from Greenland and Antarctica, from mountain glaciers in the tropics. The patterns match. The same climate shifts show up everywhere. The ice confirms itself, tells the same story from different places. This is how we know about past climates with such certainty. Not from guessing, not from models alone, from direct evidence, from air and dust and ash preserved exactly as it was. The ice is an archive, a library, every layer a page, every bubble a footnote, the whole glacier a complete history of Earth's atmosphere and climate. And glaciers are still writing this history, right now. Today's snow will become tomorrow's ice. Future scientists will drill into it and see our time, our atmosphere, our world. The record continues. The ice keeps documenting. Patient, precise, honest. Some glaciers will disappear in your lifetime. Others will persist for thousands of years. The small mountain glaciers are most vulnerable. They exist at the edge of viability. A few degrees warmer and they can't survive. Many are already past the point of no return. Glacier National Park might not have glaciers much longer. The park was named for ice that's vanishing. By 2030, some estimates say they'll all be gone. Just rock and meltwater where ice once flowed. The Alps are losing glaciers rapidly. Photos from the 1800s show vast ice fields. Now, patches. Some resorts that relied on glacier skiing have closed. The ice they built around has melted away. In the Andes, entire communities are losing their water source. The glaciers that fed their rivers are shrinking. Some have disappeared. The streams run lower each year. Eventually, some might dry up completely. Tropical glaciers will likely vanish first. Kilimanjaro's ice is almost gone. The glaciers in Papua, Indonesia, are tiny remnants. These exist in the narrowest temperature range. They have no buffer, but the big ice, Antarctica and Greenland, that will persist much longer. These ice sheets are miles thick. They hold enough ice to raise sea levels by hundreds of feet if they melted completely. But that would take thousands of years. Still, they're changing. Satellites measure them constantly. Some glaciers in Greenland are thinning. Some Antarctic ice shelves are breaking apart. The change is measurable, visible. Certain glaciers are being watched closely. Thwaites Glacier in Antarctica. Scientists call it the Doomsday Glacier. Not because it will doom us, but because if it collapses, it could trigger more collapse. It's like a cork holding back other ice. Thwaites is being melted from below by warm ocean water. The base is thinning. Cracks are forming. Eventually, it might break apart into icebergs. When it does, the ice behind it could flow faster into the ocean. This won't happen overnight. Glaciers operate on their own timescale. But it's happening. The process has started. Some scientists are proposing interventions, ways to slow glacier melting, building underwater walls to block warm water, pumping water onto glaciers to add mass, covering ice with reflective material. These ideas are controversial. The scale required is enormous, the cost immense, and some worry about unintended consequences. What if changing one glacier affects others in unexpected ways? For now, most efforts focus on understanding, measuring, predicting. Scientists camp on glaciers, drill into them, install sensors, launch satellites. They're building the most detailed picture of glacier health ever assembled. Models predict different futures depending on what happens with climate. In some scenarios, most mountain glaciers disappear, but the ice sheets remain. In others, even parts of Antarctica become unstable. No model shows glaciers returning to their size from 100 years ago. That world is gone. The ice remembers it, but it won't come back soon. Some glaciers are advancing, but not many. Perito Moreno in Argentina is roughly stable. A few in New Zealand are growing slightly due to local weather patterns. But these are exceptions. The trend is clear. Globally, glaciers are shrinking. The total ice mass is decreasing. This has been measured, documented, photographed from space. What does this mean for the future? More glacier-fed rivers will run dry in summer. Some water sources will disappear. Sea level will rise, though slowly. Ecosystems that depend on glaciers will change or collapse. But glaciers have always changed. They've advanced and retreated countless times. They've disappeared and returned. What's different now is the speed and the cause. For the glaciers that remain, life continues. They still flow, still carve, still hold their ancient ice and trapped bubbles, still make their sounds, still glow blue in their depths. They're not gone yet. Many will last centuries more. Some will last millennia. And they'll keep doing what glaciers do, moving slowly, documenting time, being patient in a world that's forgotten how. Glaciers teach patience. They move slower than anything else alive, slower than plants growing, slower than rocks weathering, but they move, and over time, they reshape continents. A glacier doesn't care about human timescales. Days mean nothing to it. Years barely register. It thinks in centuries, in millennia. It operates on a timeline so long we can barely comprehend it. This is the first lesson. That meaningful change doesn't require speed. That slow, steady pressure accomplishes what violence cannot. That patience is a form of power. Glaciers teach us about cycles. They grow, they shrink, they advance, they retreat. Nothing is permanent. Everything flows. Even ice that seems eternal is just water in a temporary form. The ice that covers Antarctica now will eventually melt. The water will return to the ocean, evaporate into clouds, fall as rain or snow somewhere else. Maybe become glacier again, maybe not. The cycle continues regardless. This is the second lesson. That change is natural. That growth and loss are both part of the pattern. That nothing stays the same forever, and that's okay. Glaciers teach us about memory. They hold bubbles of ancient air, trapped ash from eruptions, dust from deserts that no longer exist. They preserve things perfectly, keeping records longer than any human archive. But they also release these memories. As they melt, the bubbles escape. The ash washes away, the dust disperses, the past returns to the present, mixing, becoming part of now. This is the third lesson, that the past isn't separate from the present, that everything connects, that old air eventually becomes new air. That time is more fluid than we think. Glaciers teach us about scale. They're huge, miles long, thousands of feet thick. They dwarf humans completely. Stand next to a glacier and you feel small, appropriately small. But they're also made of tiny things, individual snowflakes, single crystals, microscopic water molecules. The massive is built from the minute. The overwhelming is just countless small parts working together. This is the fourth lesson, that small actions accumulate. That one snowflake means nothing, but a billion snowflakes become a glacier. That magnitude comes from repetition. Glaciers teach us about force. They're gentle, they move slowly, but they carve mountains. They reshape landscapes. They leave marks that last millions of years. Gentleness and power aren't opposites. The glacier doesn't smash or explode. It presses, consistently, relentlessly, and the mountain eventually yields. Hard rock becomes powder. Solid stone becomes a valley. This is the fifth lesson. That quiet persistence achieves more than loud aggression. That continuous pressure overcomes resistance. That you don't need to be violent to be powerful. Glaciers teach us about adaptation. Life exists in impossible conditions. Worms in the ice, algae on the snow, bacteria in permanent freeze. Life doesn't give up. It finds ways. It evolves. It persists. The glacier seems hostile to life, but it isn't. It's just another environment. And where there's an environment, life explores it, tests it, eventually thrives in it. This is the sixth lesson. That limits are often illusions. That impossible is just difficult we haven't solved yet. That life is more resilient than we imagine. Glaciers teach us about impermanence. Even things that seem permanent aren't. Even glaciers that have existed for thousands of years can disappear. Even ice miles thick can melt. Nothing is guaranteed to last. But impermanence isn't tragedy. It's just truth. The glacier doesn't mourn its own melting. It just becomes water, changes form, continues existing in a different way. This is the final lesson, that letting go is natural, that endings are also beginnings, that transformation isn't death, just change. Stand at a glacier and you feel all of this, the patience, the cycles, the memory, the scale, the force, the adaptation, the impermanence. You feel small and connected, temporary and eternal, part of something vast that's also made of tiny, simple parts. Just like you, you're connected to glaciers, even if you've never seen one. The water you drank today might have been glacier ice once, thousands of years ago, or hundreds. Water cycles through everything. Ocean to cloud, to rain, to river, to glacier, and back again. That cup of water. Those molecules could have been frozen in Antarctica when Rome was founded. Could have flowed in a Norwegian glacier during the Middle Ages. Could have melted and evaporated and travelled the world before reaching your glass today. Water has no memory of where it's been, but it's been everywhere, including glaciers. The rocks in your yard might have been carried by glaciers. If you live anywhere that was once covered by ice sheets, Canada, Northern Europe, the northern United States, then glaciers shaped your landscape. Those rounded boulders in fields, deposited by ice, the sandy soil, ground up by glaciers, the shape of the hills, sculpted by frozen rivers that no longer exist. Walk through these places and you're walking through glacier work. The land remembers even if we don't. The air you're breathing contains molecules that were once trapped in glacier ice. Bubbles that formed hundreds of years ago, sealed away, then released when the ice melted. Ancient atmosphere mixing with modern atmosphere. You're breathing history with every breath. Glaciers regulate climate. They reflect sunlight. They store water. They cool the planet. Remove them and everything shifts. Weather patterns change. Ocean currents alter. Temperature balances tip. You're affected by glaciers even if you live at the equator. They're part of the system, part of the web. Change them and the whole web vibrates. Rivers fed by glaciers provide water to billions of people. Not just mountain communities, cities far downstream, farms in valleys, industries that need water. Remove the glaciers and those rivers change, flow differently, run dry at different times. This affects everything built around them, everyone who depends on them. So even if you've never touched glacier ice, you're touched by glaciers. The species that depend on glaciers, the seals, the bears, the salmon, the ice worms, they're part of ecosystems you're part of. Everything connects. Remove one piece and the others adjust, change, sometimes collapse. You're part of this web too, not separate from it, not above it, in it. Glaciers help you even if you don't realize it. They stored water during wet years that's released in dry years. They keep mountains cold enough for certain species to survive. They create habitats nothing else creates. And they give us perspective. Standing near a glacier, you feel time differently. You see that your lifetime is brief, that your concerns are temporary, that the world existed long before you and will exist long after. This isn't depressing, it's freeing. Your problems are real but not eternal. Your mistakes are significant but not permanent. You're part of something larger that's been flowing since before humans existed. Glaciers connect us to deep time, to the ice age our ancestors survived, to the climate shifts that shaped human evolution, to the water cycle that makes all life possible. They connect us to each other too. A glacier in Alaska affects weather in Peru. Antarctic ice influences ocean currents near Africa. Himalayan glaciers provide water to people who will never see them. We're all downstream from some glacier, all breathing air that's been through the ice, all drinking water that's cycled through frozen forms, all living on land shaped by ice that came and went. The connection is invisible but real, like gravity, like air pressure. You don't see it, but it's there, always there. Right now, a glacier is melting in Alaska. That water will join a river. The river will reach the ocean. The ocean will evaporate. The water will travel as vapor. Maybe it will rain where you are. Maybe you'll drink it. Maybe it will become part of you. And you'll be connected, literally, molecularly, to ice that was formed before you were born, to a glacier you've never seen, to a system you're always part of. So here we are, at the end of our journey through ice and time. We started with snow that refused to melt, simple snow, falling and staying, building up, pressing down, transforming into something powerful and patient. We learned how glaciers flow, how they carve mountains, how they glow blue in their depths, how they trap time in bubbles, how they breathe with Earth's climate cycles. We discovered life in impossible places, worms in ice, algae turning snow pink, lakes hidden under miles of frozen weight. We followed glacier water as it feeds rivers, creates lakes, carries minerals to the sea, shapes entire ecosystems downstream. We stood beside humans throughout history who gazed at glaciers with wonder, who were preserved by them, who studied them, who depend on them. We saw glaciers that surge and store, that cling to cliffs, that cover volcanoes, that exist near the equator or hide in caves. We looked back through deep time to when Earth was a snowball, when ice covered everything, when glaciers were the world. We learned to read ice like a book, to see the atmosphere's history written in layers, to understand what glaciers remember and what they reveal. We faced the future, the shrinking, the changing, the uncertainty, and the persistence of ice that remains. We found lessons in glacier patience, in their cycles, in their quiet power, in their impermanence. And we realized we're connected to the ice, to the water, to the system, to everything. All of this from frozen water, from snow that stayed, from ice that flows. Glaciers are still moving right now. While you lie here, warm and soft, somewhere a glacier is flowing, A few inches today, a few inches tomorrow. Patient, unstoppable, following laws older than life itself. They're making sounds in the dark, groaning, cracking, singing their deep songs to valleys that have heard them for thousands of years. They're carving rock, trapping air, growing and shrinking with seasons and centuries. Being what they are, ice that moves. And maybe that's the most relaxing thing about glaciers. They just are. They don't worry, don't rush, don't question their purpose. They flow because that's what ice does under its own weight. They carve because that's what happens when ice meets stone. There's something peaceful in that certainty, that simple existence, that patient movement toward the sea. You can learn from that, the glacier way, moving slowly but moving, being patient but persistent, letting time do the work, trusting the process. Tonight, as you drift towards sleep, you can carry this with you, the image of ice flowing in darkness. Blue light in glacier caves, ancient air trapped and released, water cycling through everything. You're part of this, part of the flow, part of the cycle, made mostly of water yourself. Water that's been everywhere, done everything, become ice and vapor and rain and river and you. Let yourself be like glacier water, flowing, finding the path, not fighting, not forcing, just moving naturally downhill, toward rest, toward peace, toward sleep. If this journey brought you calm, please subscribe to Simple Science for Sleep. Join us for more quiet explorations. Leave a comment about what you learned, about which fact surprised you, about where you are in the world right now. Next time, we'll explore something else, something equally ancient, equally patient, equally beautiful. But for now, glaciers have given us enough. Let your thoughts slow like ice flows. Let your breath become as steady as snow falling. Let your body settle like layers compressing over time. You don't need to do anything. Just be. Like a glacier. Just exist. Patiently, slowly, perfectly. The glaciers will keep moving while you sleep. Keep flowing. Keep carving their slow paths through stone. Keep being what they've always been. And you can rest, warm, safe, connected to ice you'll never touch. Part of a world larger than you can see. A world that includes glaciers and you.